Welcome to Module 4 of the ABC UTC's 2015 in-depth web training on the Milton-Madison Lateral Slide Project. Module 4 is on the Milton-Madison Pier Rehabilitation Design and Construction. We're pleased to reintroduce our speaker, Travis Butz. As mentioned in Module 3, Travis is a senior engineer in the Bridge and Structural Design section of Burgess and Niple's Columbus, Ohio office. He was the lead designer of the river spans for the Milton-Madison project and served as part of the design team for the temporary and permanent approach spans and the Span D bridge slide. Travis?
Thanks, Mary Lou. Okay, so in this module, I'm going to focus specifically on the rehabilitation of the existing river piers, both from the design and the construction side. And I'll talk in detail about the design methods we used and about how we dealt with some of the setbacks we had during construction. So to review what's been talked about earlier, with the existing bridge supported by 5 river piers. And Baker did preliminary work according to those piers, and the decision was made prior to our involvement that we were going to save 4 of those piers and demolish Pier 5, the existing Pier 5, which was chloride contaminated. So proposed piers 2, 3, 4, and 5 were going to be strengthened both at the caisson level and then encased. The existing stem would be encased and a new cap would be installed, wider cap to accept the wider bridge. And then a new pier constructed up at Pier 6. So this is a graphic taken from Baker's pier strengthening report, which was part of the bid documents. And the existing piers, you can see, are founded on pneumatic caissons, which Aaron talked about how those are constructed. And those are unreinforced, and those extend from just above the river bottom down to bedrock. And that goes through about 60 feet of soil between the bottom of the river and the top of rock. And then the stem is constructed on top of those caissons, and that goes from the bottom of the river up to the bottom of the bearing seat level of the bridge, and that's about 90 feet tall. And as Aaron also discussed, that 60 feet of soil is needed to stabilize those piers. They're not stable in their existing state or in the new rehabilitated state without that soil. So it was important to consider as part of the analysis. So in order to support these new loads, we needed to strengthen the caisson. This slide is the strengthening as conceived by Michael Baker pre-bid. So that was to drill holes into the caisson, install rebar into the caisson down to the level where we needed to resist tensile forces in the caisson. Grout those bars into place and then add reinforcement up at the stem level, encase that existing stem in concrete, build a reinforced pier cap to accept the wider superstructure at the top. So this was the concept prior to the bid and our involvement in the revised maintenance of traffic scheme. So after we won the job and proposed the new MOT scheme, we had to incorporate that into the pier strengthening sequence. So we had these new existing pier towers that were going to need to be connected to the existing piers for stability and to make the bridge slide possible. We need to have the sliding girder in contact with the existing pier to allow the bridge to be slid over into place. So they were going to play into how that strengthening happened, and the next few slides take you through the sequence we propose to make that happen. So the existing condition of the pier is on the left, so you can see where the water level, the bottom of the river, the top of the rock is, and then the existing pier stem. And the first step in the strengthening was going to be to install a cofferdam around that pier stem and dewater it, and then perform that caisson strengthening, which was getting down there, drilling holes in the caisson, dropping in rebar and grouting them into place. The next step was to then construct the encasement concrete up from the top of the caisson up to the bottom of the proposed pier cap. So once we've got that done, so you can see the new concrete here. Once that is in place, we can remove that cofferdam, so we no longer need access to the caisson. And then that allows us to install the temporary pier, which is braced to the permanent pier for barge impact. And then we're going to install the sliding girder and the new truss in the temporary position. And this again skips over a lot of interesting stuff, which Murray will discuss in the next presentation. And we're also at this point still maintaining traffic on the existing bridge. And at this point, we switch traffic over to the proposed bridge, remove the existing truss and the existing top of the pier, and then we can partially construct the new pier cap. We can't fully construct it because the sliding girder bears on what's called the sliding girder pedestal here and obstructs part of that new pier cap construction. The sliding girder is shaped like a tuning fork at this end. It wides out and misses the middle part of the pier cap to make the slide possible. And the next slide shows that in plan view. You can see the sliding girder coming over. It's got two beams that are attached onto the main girder that bear over on the sliding girder pedestal, which is part of the pier cap. And then you can see the truss bearing. This is the right truss bearing in the temporary position, which is just adjacent to the left truss bearing in the permanent position. So when the slide happens, cross that gap and move the truss over right along that center line of the pier. So now we can proceed with the slide. We move the bridge over, lock it down, and then that allows us to remove all this temporary material. And once that's out of the way, we can complete the construction of the pier cap. And during this process, we're also installing the riprap scour protection around the base of the pier, which prevents that essential material from ever scouring away to make the pier unstable. So when we designed these piers, we had to consider the effects of that construction sequence. So we had all the usual forces on the pier. We had wind, we had traffic loads from the bridge, braking force. We also had barge impact to consider, but on top of that, we had to think about, is this bridge slide going to create forces that we need to design into the piers? When we looked at the slide, we considered a couple different options. We considered pushing the bridge over from the temporary pier, and we considered pulling it from the permanent pier and pulling it over from the temporary pier to the new pier, or to the rehabilitated pier. And both those two methods had different implications as far as forces that would be imparted on both the temporary and the permanent pier. And what we ended up deciding to do was pulling it. We would use a strand jack from the main pier and pull it across from the temporary to the rehabilitated pier. And we were going to use PTFE sliding bearings to slide the bridge on a smooth steel surface from one pier to the other, and that's analogous to a furniture slider used to shove heavy furniture around on a smooth floor. So this is an analogy I think helps you understand the forces that are involved. Um, if you look at the diagram to the left, the safe in this diagram represents the truss. So it's over on, and it's sitting, this left table represents the temporary pier, and the right table represents the permanent pier. And this guy represents the strand jack. So when the slide occurs, he's going to pull on the rope, his feet are going to push on the table. The safe is going to push back with friction against this other table. As long as those two tables are in contact, those two forces oppose each other without imparting any net force on the table legs. So what you end up with is a net compression across the tabletops. So when we slid the bridge over, what we had was a net compressive force across the sliding girder and the cap of the permanent pier. So we didn't have any net force effects we had to consider on the design of the caisson strengthening or the stem reinforcement. So moving on to how we carried out that pier analysis, and we used a well, again, you had to consider that we had to include that sandy soil below the river bottom in the analysis, and in order to account for the restraint that provided, we used a global analysis that included the soil surrounding the pier. So you can see we used this three-dimensional finite element model that considered soil for, I think it went about 300 feet around the perimeter of that pier. And we did this in Midas GTS, and we modeled the pier in both its temporary existing condition, in the partially rehabilitated condition, and in its new fully rehabilitated condition. So you can see an elevation of that pier. This is partially rehabilitated with the existing caisson, the pier encasement, and the existing cap in place. And this is the fully rehabilitated pier with the new cap in place. And these models included friction interfaces with the surrounding soil, and also included the properties of that surrounding soil. And we used the output from the model for several different things. So this is a rock pressure diagram, and we use this to identify peak pressures generated by the different load combinations on the pier. This is for the bedrock below the bottom of the caisson. So we're obviously adding quite a bit of load to that caisson, and we were also adding a good bit of wind exposure. So we use this to make sure we weren't going to overload that rock to the point where it could have created a problem below the base of the caisson. And we also used the model to look at the concrete stresses in the existing caissons. These caissons were originally unreinforced, and the design criteria required that we add reinforcement anywhere where we had net surface tension in the caissons. So we used this output to determine how deep we needed to install that reinforcement into the caisson. And we also used the output to locate a fixity point for the pier foundation. In addition to the finite element analysis, we also did a conventional column analysis for the pier stem and the caisson. And to do this, we had to establish a fixity point so we could calculate the peak moments in the caisson. And the way we did this was we located the peak tension point in the caisson along the surface of the, and we used diagrams like this to define that point and measure how far it fell below the top of the caisson. And then we would pull that number and use it in our analysis, in our column analysis of the pier. So this is a shot of that strength analysis. When we did this once we had the fixity point, we calculated the axial loads and the biaxial moments on the pier stem and in the caisson. That included all the various loads, the dead load and live load from the truss, the wind, barge impact loads, braking loads, and any loads coming also from the temporary pier construction. And then we created an axial moment interaction diagram here on the right, which we used PCA column to do that, and use that to design the reinforcement in the caisson and in the pier encasement. So the next few slides are going to take you through how these piers were constructed. This is going to go through the sequence we discussed earlier, and you can see here this is the first phase. This is the installation of the sheeting around the base of the pier, and you can see the pump in action to dewater the caisson below. And this is a shot from inside of that cofferdam after it's been dewatered. And you can see here the base of the pier stem and the top of the caisson. And if you look closely at the top of the caisson, you can see there's something unusual going on here, which is the first of several surprises we had when we uncovered these caissons. This is the edge of the caisson, and this is a timber that was embedded at the top of that caisson. And beyond, on the backside of that timber is a raised portion of the caisson. So the caisson both had a timber embedded and was stepped at the top, which made for an irregular surface that didn't lend itself to coring holes in. So in order to work around this, we had to remove those timbers and then construct a new concrete collar around the top of the caisson and use that new level surface to do our coring for the holes for the reinforcement. And here's a photo of that coring operation. The holes extended up to 71 feet 7 inches below the top of the caisson when we were drilling these in. And that was based on the tension results from our analysis. And this coring operation led to our second surprise during construction, which is that we expected these caissons to be solid concrete. We found there was a lot of material embedded in them. There were wood timbers and there were steel form supports that we hit as we cored down, and which greatly slowed the progress of the coring. So the average progression of the coring was about 4.5 feet per hour. And if you look at the picture on the right with all the extracted cores, you can see how many feet of coring that involved. So this was a slow process to get all these holes drilled and the rebar installed. Once we did get the holes cored, we were lowering in bundled number 11 and number 14 bars down those holes. And since the length of some of those holes exceeded the length of bars we could get, we were also using mechanical connectors. We had to stagger those mechanical connectors to make the bundle tight. We were lowering those down the holes. With the bars, we sent grout tubes down the holes so that when we installed the grout in the holes, it got pumped in from the bottom up. And as part of that grouting operation, we uncovered another unpleasant surprise, which we discovered that we were putting more grout in the holes than there was hole to put grout in. And sometimes when we grouted one hole, the hole next to it would also fill with grout. So this indicated that there were voids somewhere in the caisson that were interconnecting the holes, and that raised some questions about both the validity of our analysis and the capacity of the caissons. So this, if you'll recall, Aaron's presentation about how those caissons were constructed. They lowered down a metal chamber that was a steel chamber that they used to excavate the material at the bottom of the river down to rock. And once that they reached the bottom of the river, they filled up both the access tubes and the chamber with concrete. And we thought maybe the voids we were encountering were related to that steel chamber. This diagram shows the caisson in its existing state with holes cored in, and those holes were going to come down just below the top of that chamber. And we suspected that when they filled that chamber with concrete, it was possible that an air void was left just inside that chamber, and if the holes were hitting that void, that might be where the interconnection of the holes was occurring. So there was a good bit of debate and investigation into the cause of those holes. There were cameras lowered down the holes to attempt to assess how bad the voiding situation was. The results of all this were somewhat inconclusive. We could see some voids, but it's hard to tell exactly what was going on. So in order to keep things moving, the decision was made to continue coring and grouting, and we would just attempt to fill any existing voids with grout as we progressed. And then once all those holes were grouted, we drilled test holes and to test to see if we were finding any voids in the fully grouted caisson. And the results of those appeared to be that the caisson was solid at that point, so it appeared that that strategy worked. So once we did get the caisson reinforcement installed, we moved forward to the pier strengthening. And here you can see the stems prior to encasement. We're drilling in shear connectors around the entire surface of that pier. Those are on a 2-foot grid. And we're drilling in those hooked bars to engage the new concrete with the existing pier stem. And then we're constructing the new encasement rebar around the perimeter of that stem. And we're going to put the formwork up and encase all that from the top of the caisson up to the bottom of the proposed cap. So you can see here the rebar for the upper portion of the pier stem. This is the portion that carries the loads from the sliding girder, which supports the truss in its temporary position. And the loads in this part of the cap are extremely high because of all that force from the truss. You can see tight reinforcement here at the top of the stem, and then these vertical bars sticking up are going to go to the sliding girder pedestal, which is the concrete pedestal that supports the truss. And here you can see the completed pier stem. The temporary pier is in place, and the rebar for the sliding girder pedestal is set, and it's ready to be poured. And you can see there's quite a bit of rebar in this pedestal because of the forces that it experiences. Here's a close-up of that pedestal. I think there's just about as much rebar as there is concrete in that pedestal. It's got about as tight as you could pack it in there. And that's because that tuning fork girder is going to sit on either side of this pedestal, and then all of the wind loads, the lateral loads that truss experiences are going to get drawn over to this permanent pier because it's so much stiffer than that temporary tower. Now you can see the sliding girder and the truss in place. And we're in the process of forming the permanent cap. And you remember the end of that cap is constructed in a T shape because of the interference of the sliding girder when it's initially cast. You can see those blocked out areas of the pier cap here. Here's a top view of the pier forms. This is taken from the new truss in the temporary position. And you can see that T-shaped nose of the pier sticking out here. And you can also see at least heavy supports that were necessary to hold up the bearing plates and all the embedments in that pier cap that were needed for the slide and for the permanent truss position. So now the cap is poured and the slide's underway. And you can see the cap is still unfinished on the right side. And it has to stay this way until the bridge is in its permanent position, in which case we can put the final closure pours in place. And here's a shot that shows the piers in their finished condition and the sliding girder pockets filled in. So lessons learned, expect the unexpected when you're doing rehabilitating an existing bridge. So, you know, a lot of things were uncovered as we dug down into those caissons that slowed our progress. So don't expect things to go according to plan. Anticipate problems to what degree that is possible. I think we were successful in doing this with some things, but less successful with others. I think it's valuable to spend some time considering what might go wrong in a project like this. And be flexible. We had to do this a number of times, listen to the people in the field and everyone involved and come up with the best idea you can to solve these problems as they come up. So again, I want to thank Walsh and Charlie Gannon and Deborah Crawford for the photos I used in this presentation, and also the graphics from Michael Baker and Buckland Taylor. And with that, I'll take any questions.
Thank you, Travis. We'll now begin the Q&A session. So any participants, if you have additional questions, please type them into the question box. So first we'll begin with a question. Did the analysis consider soil structure interaction, and if so, how was the soil modeled?
Yes, it did consider soil structure interaction. We used Midas GTS software, which considered the soil properties and also the friction interface between the soil and the concrete in the existing piers. So that was critical to the stability of these piers. And as a lot of that work was started by Michael Baker before our involvement, and they did a lot of verification work between that finite element model and more conventional analysis types like L-pile, that type of analysis.
Okay, thank you. And what was the controlling load case for the design of the caisson strengthening?
It depended upon the pier. Some of them were, I think the fixed pier was controlled by wind, longitudinal wind on the structure, and the others were controlled by barge impact loads.
Okay, and so far, this looks like the final question. Was conventional analysis of the pier foundations performed in order to validate the results of the finite element modeling?
Yeah, that going back to the first question, yes, that was actually done prior to our involvement by Michael Baker. The type of analysis we did was mandated by the scope of the project, and they did validation of that analysis type with L-pile and conventional software before our involvement.
Okay, thank you. We're now at the end of we don't have no more questions, so we're now at the end of the fourth 40-minute module. Thanks again to you, Travis, Butz, and to all our participants in this fourth module. And remember, if you have additional questions, Travis has said you can feel free to contact him directly.